Okay, let's unpack this. There's a fascinating piece of research that recently came out from Apple, and it's sparking a pretty big question.
Oh, yeah. What's that?
Is a lot of what we've been calling AI reasoning potentially just an extremely sophisticated form of pattern matching?
Ah, right. I saw that paper mentioned. It definitely throws a bit of a curveball into the whole AI hype cycle, especially around AGI.
Exactly. Artificial general intelligence. And
Yeah.
what's really interesting here, I think, is that this isn't just some philosophical debate.
No, it's based on actual experiments, right, from their machine learning team.
Precisely. They designed this whole setup specifically to test whether these leading AI models truly think or if they're mainly just incredibly good at recognizing patterns.
Which is a crucial distinction.
It really is. And for this deep dive, we've gone through the study itself, looked at some news reports, analyses discussing what it all means.
Okay.
Our mission really is to dig into how they designed this unique experiment, what their findings actually show about where these models stand today, and what that suggests about how close we really are to AGI.
Sounds good. So, where do we start? The motivation. Why did they even feel the need for a new kind of test? What's wrong with the usual benchmark?
That's the key question, yeah. The standard ways we test AI, like complex math problems, coding challenges, general knowledge stuff, they have this big potential issue.
Data contamination, you mean?
Exactly. Data contamination. These huge models, they're trained on just unbelievable amounts of data scraped from everywhere online. Books, articles, websites, code.
So it's almost impossible to know if they've already seen the test questions or something very, very similar during that training phase.
Right, so you give it a coding puzzle and you think, wow, it solved it. But did it reason through it? Or did it just kind of remember a pattern, a solution structure it saw somewhere in that massive training data set?
It's hard to tell the difference then, like a student cramming answers versus one who actually understands the subject.
Perfect analogy.
Hmm.
The traditional tests often can't cleanly separate those two things, genuine understanding versus really good memorization or pattern matching.
Okay, so Apple needed a way around that. To test pure reasoning without that contamination risk, what was their approach?
They came up with something pretty clever. Controllable puzzle environments.
Controllable puzzles. Tell me more.
Basically, structured, rule-based games or problems where the researchers have total control. They can generate specific instances of these puzzles that they know weren't floating around on the internet for the AI to memorize.
Ah, I see. So a clean testing ground. Were these like brand new puzzles they invented?
Not necessarily invented, but carefully chosen classics known to require logical reasoning and planning. Think Tower of Hanoi,
Okay, yeah.
checker jumping puzzles, river crossing problems, blocks world, stuff like that.
Right, the kinds of problems with simple, clear rules, but that can get surprisingly complex.
Exactly. And the key thing is, you can scale the complexity very precisely.
Hmm.
Add more disks to the Tower of Hanoi, more items in the river crossing puzzle.
And that lets you see exactly where things start to break down.
Precisely. You can pinpoint the level of logical steps or complexity where the model's performance changes. It lets you really probe the limits of their reasoning in a controlled way.
Okay, that makes sense. Clean, scalable problems designed to isolate the reasoning part. So which AIs did they actually test? Was it the standard chatbots or something else?
They focus specifically on what the paper calls large reasoning models, or LRMs.
LRMs. Okay, what defines those?
These are the models often built on top of large language models like the ones we interact with, but they're specifically designed or prompted to generate sort of internal thinking steps before giving an answer.
Like chain of thought prompting, where you ask it to think step by step.
Exactly like that.
Hmm.
The whole idea is to mimic a reasoning process. They tested variants of models like Claude 3.7 Sonnet, DeepSeek R1, OpenAI's O3 Mini, basically state-of-the-art examples of this reasoning approach.
Got it. So the best contenders designed for thinking, tested on clean logic puzzles with increasing difficulty. What was the big headline finding? What happened when they cranked up that complexity dial?
This is where it gets really striking. The most consistent finding across all the different LRMs they tested was that they hit what the study calls a complexity wall.
A wall, like performance just gradually got worse.
No, much more dramatic than that.
Yeah.
Beyond a certain point, and this point varied a bit depending on the puzzle type,
Hmm.
the model's accuracy didn't just sort of dip, it completely collapsed.
Collapsed? To what?
0%.
Zero. Wow.
Mm.
Across the board. For models designed for reasoning, that sounds significant.
Hugely significant. And the study explicitly notes this collapse happened no matter how much computing power you give them or how long they tried to how many tokens they use for their reasoning steps.
So it wasn't just a matter of needing more time or resources, it was something more fundamental.
That's what it strongly suggests. A fundamental limit in handling that level of logical complexity, regardless of scale or effort.
Huh. That really cuts against the common idea that you just need bigger models or longer thinking time, right? It's like that House of Cards analogy you sometimes hear.
Yeah, it feels very appropriate here, looks impressive, maybe even stable up to a point,
Right.
but add just one piece too many.
And the whole thing doesn't just wobble, it completely falls apart.
Exactly. Fragility when the logical chain gets too long or complex.
Okay, so they hit this hard wall at high complexity. But what about before that? Was it just smooth sailing until the collapse?
No, and that's another really interesting layer. They found performance wasn't just like linear. They identified three distinct regimes based on the complexity level.
Three regimes. Okay, walk me through them. Low complexity first.
At the really low complexity end, the simplest versions of the puzzles, something surprising happened. The standard models, the ones without the explicit chain of thought or thinking steps, they often did better than the LRMs.
Better. How so?
They were more efficient, used fewer compute resources, tokens,
Huh?
and got the right answer more quickly and accurately. The LRMs, the thinking models, sometimes showed what the researchers called overthinking.
Overthinking. What does that even mean for an AI?
It means like maybe the model figures out the correct first step or even the whole path quite early in its generated thought process.
Okay.
But then it keeps going, exploring other paths that are wrong or adding lots of unnecessary validation steps.
Yeah.
It found the answer but kept churning inefficiently.
So for the really simple stuff, that extra thinking layer actually just got in the way sometimes? Added noise or wasted effort?
Seems like it. The more direct pattern matching approach was just more effective when the task was straightforward.
Interesting. Okay, so standard models win on easy street. What about the middle? Medium complexity.
Right, this is where the LRMs, the thinking models, started to shine. In that medium range where problems needed maybe a few more logical steps, a bit more planning,
Yeah.
that's where the chain of thought process seemed to provide a real benefit. It helped the models navigate those intermediate hurdles better than the standard non-thinking versions. The performance gap favored the LRMs there.
Okay, so thinking helps when things get moderately tricky. Makes intuitive sense. And then regime 3 is where we hit the...
The high complexity regime, and like we said, that's the collapse zone. Utter failure for all the models they tested, whether they were standard or LRMs.
So even the thinking models just couldn't handle the really tough versions. Maybe they pushed the wall back slightly further than the standard ones, but they still hit it hard.
Exactly. They might have eked out a slightly higher complexity threshold before failing, but they still failed completely, 0% accuracy.
Okay, so if you're listening and trying to map this to using AI tools, it sounds like. For simple tasks, basic models are fine, maybe even better. For moderately complex things needing a few logical steps, maybe use a model with a thinking feature, like chain of thought.
Could give you an edge, yeah.
But for really deep, multi-step, truly novel logical reasoning that isn't just recalling a pattern, this study suggests current models.
Yeah.
Well, they just don't cut it. They hit a limit.
That seems like a really practical takeaway. Sets more realistic expectations based on what they saw in these controlled tests.
Definitely. Now, you mentioned something earlier about counterintuitive finding related to how much they thought as things got harder.
Yes. This was one of the weirdest parts, I thought. You'd naturally assume, right, that as a problem gets tougher, a model trying to reason would, well, try harder.
Yeah, spend more effort, generate a longer thought process, explore more options. That seems logical.
And initially, that's sort of what they saw. As complexity increased from low to medium, the models did tend to use more tokens, generate longer reasoning traces.
Okay, that fits.
But UT fits.
Yeah.
As they got closer and closer to that specific complexity level where they hit the wall, the point of 0% accuracy. They observed the models actually started using fewer thinking tokens. They generated shorter, less detailed internal reasoning steps, even though they still had the token limit to keep going.
Wait, hold on. They started thinking less right when the problem was getting hardest and presumably needed more thinking?
Exactly. That's completely counterintuitive. It doesn't sound like a system diligently trying to work through a difficult logical puzzle.
No, it sounds odd, almost like it gets overwhelmed and just gives up faster. Or the process itself breaks down.
That's what the study suggests. It hints it's not just about hitting a token limit, but maybe a fundamental problem with their reasoning method. When the complexity exceeds a certain point, their internal process seems to falter, leading to these shorter, ineffective attempts.
Like getting stuck in a loop or just failing to generate meaningful next steps. Yeah,
Yeah.
that's strange. Not like a human who keeps trying, maybe messily, but keeps trying.
Right. It's more like they doodle for a bit and then stop before the really crucial steps even begin.
It really points towards the current thinking process not being a truly robust, scalable method for complex logic.
And adding to that picture, reinforcing these limitations, the researchers did another really telling experiment about following instructions.
Ah, yes, the algorithm test. This one was fascinating.
So they took a puzzle, like Tower of Hanoi, right? And instead of just saying, solve this, they gave the model the exact algorithm, the step-by-step, guaranteed to work instructions to solve it perfectly.
It's like handing someone a perfect, tested recipe for a cake.
Exactly. Now, you'd think if these models are good at processing language and instructions, giving them the perfect algorithm should make them ace the test, right? Especially compared to figuring it out themselves.
That would be the logical expectation. If you give it the how-to, it should just do it.
But that's not what happened. The really surprising finding was that the models still failed at roughly the same complexity points, even with the perfect algorithm spoon-fed to them.
Still failed. So providing the exact steps didn't significantly improve their ability to solve the harder versions.
Nope. Their performance wasn't much better than when they had to figure out the logic on their own.
Wow. So even with the perfect recipe, they still burn the cake at step 5, just like before. That implies.
It implies a limitation not just in finding the logical path, but potentially in executing it reliably step by step when things get complex, even when the steps are laid out explicitly.
That raises serious questions about their ability to handle precise computation or follow methodical, rule-based procedures beyond a certain complexity threshold. It's not just about discovery, it's about execution, too.
Yeah, it really undermines the idea that they can just reliably follow any complex logical instructions we give them.
Absolutely. And there was another piece of evidence pointing towards this pattern matching idea over general reasoning, wasn't there? Comparing different puzzle types.
Right. The huge difference between Tower of Hanoi and river crossing.
Yeah, that was stark. Tell us about that.
Okay, so on Tower of Hanoi puzzles, the models could actually handle problems requiring over 100 correct moves before they started failing significantly. Pretty impressive, right?
100 plus moves. Yeah, that sounds decent.
But then they tested the same models on river crossing puzzles. Different rules, different logic needed.
Yeah.
And on those, they completely collapsed after only making 4 or 5 correct moves.
Oh, from over 100 moves on one puzzle type down to just 4 or 5 on another, that's a massive performance gap. How did the researchers explain that?
Their interpretation leans heavily towards memorization or exploiting patterns learned during training. Tower of Hanoi is a super common problem in computer science education, textbooks, online examples.
So it's likely all over their training data.
Exactly. The models might have effectively memorized solution patterns for Tower of Hanoi. But river crossing puzzles, while also classic, might be less ubiquitous in the data.
Meaning they couldn't rely on a learned pattern and had to use more general reasoning, which they apparently lack.
That seems to be the strong implication. They fail quickly when faced with a less familiar structure that requires applying logical principles more generally, rather than recalling a specific learned procedure.
So it suggests they're not learning the general principle of how to solve logic puzzles, but rather learning solution templates for specific puzzle types they've seen a lot of.
Yeah, recognizing the specific problem type and applying a remembered pattern instead of truly reasoning through the novel constraints of a particular instance.
Okay, so when you put all these pieces together, the complexity wall, the collapse to zero, the weird shrinking thinking, the failure to even follow an algorithm, this big puzzle discrepancy, what's the big picture message for the whole AI field and those AGI claims?
Well, it seems to seriously pump the brakes on the more extreme hype, doesn't it?
It certainly pushes back. While everyone agrees these models are incredibly powerful in many ways, this study directly challenges the narrative that the reasoning we're seeing is true, generalizable intelligence.
Or that just making current models bigger, throwing more data and compute at them, will magically fix these fundamental limits.
Right. It suggests that simply scaling up might not be enough to get past this complexity wall. We might need something more fundamental.
It feels like, while some headlines are talking about sparks of AGI or models thinking, this Apple study provides pretty solid empirical evidence saying, hold on, a lot of that looks like really, really good pattern matching that breaks down under pressure.
And it implies we might be quite a bit farther from AGI than the hype suggests. It shifts the conversation maybe from just scaling to needing actual architectural or algorithmic breakthroughs for robust reasoning.
Do they look inside the thoughts, too? Like the actual step-by-step reasoning traces the models generated?
They did, briefly, and analyzing those traces kind of backed up the overall picture.
How so?
At low complexity, you saw that overthinking, finding the right path, but then wandering off. At medium complexity, the traces showed exploration, maybe going down wrong paths, but eventually finding the correct one. Sort of a messy but successful search.
Okay. And at high complexity, where they failed?
The traces themselves were just flawed. They simply didn't contain the necessary logical steps to get from the problem to the solution. The internal process itself was breaking.
So the failure wasn't just getting the final answer wrong. The supposed reasoning process itself fell apart.
Exactly. The internal evidence matches the external failure.
Okay, so let's boil this down for everyone listening. How should this study change how you think about or use the AI tools you encounter every day?
Well, the first thing is not to suddenly think these models are useless. They're absolutely not. Their pattern matching ability across huge data sets is phenomenal for tons of tasks.
Right, like writing emails, summarizing text, generating creative content, even coding assistance, stuff they're great at.
Exactly. They are incredibly powerful tools within their actual capabilities. But this study highlights where the limits are.
Specifically in that complex, novel, step-by-step logical reasoning area.
Precisely. So the key is realistic expectations. If you need something that requires really deep multi-step deduction, or you need absolute certainty that a complex algorithm is followed perfectly, well, this study shows current models hit hard limits there.
So don't mistake fluent text that sounds like reasoning for actual, reliable, deep thought, especially on complex, unfamiliar problems.
That's the core message, I think. Don't assume they can solve any arbitrarily complex problem just by thinking harder, because this evidence suggests their current thinking process has fundamental scaling issues.
Appreciate their strengths in pattern recognition and generation, but be cautious and critical when it comes to tasks demanding true, flexible, step-by-step logic. Always verify important outputs.
Couldn't have said it better. It encourages a more grounded, critical view of what AI can and, maybe more importantly, cannot reliably do right now. It's a dose of empirical reality amidst the hype.
Absolutely. This has been a really fascinating deep dive into this Apple research. Using those controlled puzzles, they've provided some pretty compelling evidence that today's AI models hit a hard wall with logical complexity.
Yeah, suggesting that reliance on pattern matching over truly generalizable reasoning, it definitely challenges those optimistic AGI timelines.
And those details, the three regimes, that weird shrinking thinking, failing the algorithm test, the puzzle differences, they all paint a consistent picture of limitations, not easily fixed by just more data or compute.
It really points towards needing new ideas, new approaches.
Definitely gives you a lot to chew on about what these systems actually are. Which brings us nicely to our final provocative thought for you, the listener, to maybe mull over.
All right, let's hear it.
If these leading AI models, the ones designed for reasoning, struggle to even reliably follow a perfect step-by-step algorithm when a problem gets complex, what does that really tell us about the fundamental nature of their current intelligence? And maybe more importantly, what kind of foundational shift, what sort of breakthrough is really needed to get AI beyond this incredibly sophisticated pattern recognition towards something we could genuinely call flexible, scalable, and reliable reasoning?
That's the billion-dollar question right there. It really defines the edge of AI research today.
Indeed it does. Well, thanks for joining us for this deep dive. We hope it offered a clearer, maybe more nuanced perspective on AI reasoning as it stands today.
Always a pleasure to dig into the details.